Welcome everybody to our final session of the winter and spring series of the Laws of Nature seminar series. Today we're very happy to have Volker Bach here, and we'll do our usual procedure. So I only say hello and then I hand over directly to our moderator, Paula, who will guide us through the session today.
Okay, thanks, Dirk. So welcome also from my side. So this is the last session of this winter term, and again we will have a talk that is made of a perspective part, which is about 20 minutes. Then we have a 2 minutes break if there are any questions to that, and then we have the core talk, which is more technical, about 45-50 minutes with a Q&A afterwards. So I'm happy to announce the first speaker. I'm happy to announce the speaker of today, Volker Bach. So he's a mathematical physicist, mathematician working in analysis, and he's employed at the Technical University of Braunschweig. So I'm happy that you come here today, and I'm looking forward to the talk. It's about the effective description of many particle systems. So please, you can start.
Okay, so first of all, thank you very much, Paula, Dirk, and Fabian, for the kind invitation to give this seminar talk in the Laws of Nature series. It's in fact, I think, a great idea and quite an honor, and maybe even a bit intimidating to speak here. But anyway, let me proceed. So we start with the perspective part. And I have set up a presentation. Let me just ask in the first place, can you see the presentation?
Yes.
Should be visible? Yeah. Mm-hmm. All right. So here it is. I would like to first, in this perspective, I would like to describe what is an effective theory. I'd like to point this out, and I do this on two examples. One is dynamical, and the other example is static. So the first example is the dynamical one. So I suppose I want to study a system. It could be in physics or in general natural sciences and technology or economy or you name it, medical sciences, whatever. It's a very general approach. So we have a system that we want to study, and the state of the system is determined by a large number of variables. So I have n variables that I put together in a vector x underscore, and the state at t non-zero, non-negative, is given by x underscore of t. So this is a huge vector, and the dynamics of the system is then given by some equation of motion. What this equation of motion is depends, of course, on the system that we want to study. So, but the general structure of this equation of motion is the one I describe in equation 1. So we have it's a ordinary differential equation, an evolution equation. In fact, it's first order. So the derivative of our variable vector x of t is given by some function f of x of t. I assume there are no external influences and no explicit time dependence. For simplicity, all this could be also taken into account, but let me not do it. I want to convey the general idea. So x dot is f of x, and then we have an initial value at t equals 0, which is x naught, and then this is an initial value problem. This is what is known in mathematics as an initial value problem. It has been studied for centuries, and conditions that guarantee the existence, the global existence of a solution and its uniqueness are well known and well understood in various important contexts. So this is not my concern. I assume that we have done this. Let me focus on the bottom line. The full description of the system by equation 1 and the solution is, however, too detailed. We don't really need to know these values of x of t, in particular if n is vast. So think of Avogadro's number or even larger numbers, 10 to the 24. And so it is not necessary, and also it is impossible to follow the trajectory. And here is where the idea of an effective theory comes in. So for most applications that I know of, the full knowledge of the vector x of t is not necessary and not desired, in fact, either. And in fact, it suffices to follow a few average quantities, to follow the evolution of a few average quantities that I call y of t, in again comprised in a vector y1 of t through ym of t. But m now is a number which is much smaller than n, so we have much less variables. So typical examples I have in mind, even though the dimensions don't really match here, don't look at this too closely. So typical examples I have in mind are the mean position of the particles, the center of mass, if you want, and the variance of their positions. How much are the particles, if we think of particles, spread about the mean position? So these are typical choices for average quantities, and in general one can say that these j of t are functions of the original variables. We can derive them. But then the really interesting question is, can we derive y of t from y of t alone? Or do we always need the many other variables that are not taken into account? So can we write, again, an initial value problem of y of t? So y dot is equal to some function j tilde of y, and some initial value. So posing this question, I can say the answer is in most cases no, it's not possible. And maybe that's already an interesting thing to look at. Namely, one can see that for most examples, if you are trying to quantify an equation of motion for a reduced set of variables, then it will not be possible to put it in a differential equation anymore. It will be an integral differential equation, and the right side of the equation of motion, where I had the g tilde here, the right side does not depend only on time t, but on the entire path between t equals 0 and then the t we are looking at. So. But then, if it's not possible, then we are more modest in our goals, and we search for an approximation. So we look for quantities y approximate of t, again, a few variables, and they follow some equation of motion, and we hope that this evolution captures the main feature of the full evolution of the system we had before. So this defines an effective theory, and the variables y I would then call effective variables. Now, two main questions naturally arise if we follow this program. First of all, we have to be able to control the error made by the approximative y. So y approximative, if it agrees with y at time equals 0, then can we control the error for positive times? That's a natural question. And if this error is small, then we had made a good choice for y. So this is kind of a quality measure. And then suppose that we can give to an affirmative answer to A, then it is interesting to study Y in its own right. So we study the dynamics given by the equation 2, and we analyze the solution. So, for example, for large times, this would be some sort of scattering theory, perhaps. It would be it is interesting to see what sort of solutions, what is the behavior of the solutions, and then can we conclude something from the original problem from this. So there is, however, a disadvantage or price to pay when we pass from the x variables to the y variables, namely the structure of the equation 2 is typically more complicated than the structure of the original equation. So what happens is usually that the equation 2 is nonlinear in y, and worse, it's usually non-local, so it's not a differential equation on the right side anymore. If we had originally partial differential operator, it will be something non-local, say a pseudo-differential operator at best. And this is the case even if the original equation is linear and local. You know, so we pay this price. All right, so let me come to the second example in this introduction. It is similar, but I want to study a static case because this is, in fact, what is going to be my focus in the main talk. So the second example is again about a general system in natural sciences, technology, or economy. And I assume that the state of the system is determined in principle from the original model by a large number of variables in a vector x underscore. And the value of these variables is determined by a minimization problem, by a variational problem. So we have some functional E, which in physics is usually the energy, but in economy is perhaps the costs, or whatever one wants to do. Information theory could be information loss, or whatever. So in any event, we want to minimize a functional of the many variables we have, and the infimum of this functional we call the ground state energy, EGS. So then, again, we pass to average quantities, y, the y1 through ym, m being much smaller than n. And these quantities derive from the original variables by some functions capital Y1 through capital Ym. And then we also design an auxiliary functional EOX, which again serves us to formulate a variational problem. So we have an auxiliary energy, E auxiliary, which is the infimum of all values of the auxiliary functional on the variables y. And the minimizer is then what we think the correct value of y is. So again, we have main questions that arise here. Namely, first, can we control the errors of the functional, of the functional or infima of the functionals? There is the original function we wanted to minimize, the cost function or energy function, EGS, and then there's the approximation, the auxiliary functional, the infimum of the auxiliary functional. We want these two numbers to be close to one another. And if that is, I mean, I have to say, for many problems, this is all one can do. Yeah? But for some problems, if they're not too complicated, we can even ask for whether the variables y, these average quantities, are also close to one another. So those values of y that we get from the full theory, and we compare it to the auxiliary theory, and then hopefully the value is also small. So this is measured really by a norm. It's not an absolute value. And again, if we have small errors here, then the choice of y as effective variable is good. And once we have, so to say, checked that the error is small, then we can proceed to analyze the auxiliary energy functional and its minima in their own right. So we are interested in the predictions obtained from the minimizer, namely what is the actual value of the auxiliary energy? Can we compute it explicitly? And often the quantities, the original quantities, like the ground state energy, is well defined, but there's no series expansion or anything available that we have. And then we would like to know how the minimum, what is the behavior of this minimum as we are close to the minimizing configuration. So as y varies about the auxiliary y, the minimizer, how does the energy functional vary? So this leads to the question, are there perhaps degeneracies, large degeneracies of these minima? No, this is, by the way, also something that is often the case for these effective theories, and they have some implication on phase transitions then for the full systems, at least on physically. Whether mathematical rigor is given here or not is usually not so easy to decide. So then we are also interested in predictions that we can derive from this auxiliary functional. So do we have, if we study a system in condensed matter physics, can we derive some long-range order of the system? If we can do it for the full theory with 10 to the 24 particles, can we at least prove that there is some, say, for example, magnetic ordering for a system in this effective theory? So it has some importance in its own right. So that is what I would wanted to say for the perspective.
Okay, thanks a lot. That was a very nice introduction to the field, I think. Is there any immediate question? I mean, if there is any question on this outline, basically, you can ask it now. Okay, Dirk, you want to ask or comment?
Yeah, but I can also wait for the audience. I mean, I'm usually the one who asks first, but I think there's no question in the audience so far. So, Volker, let me maybe ask a little bit about the between equation 1 and equation 2, the microscopic and the macroscopic. So, do you say the y are, I understand correctly, are the moments or the empirical moments of the x coordinates? Is that correct?
That could be, yes. We will come to, I mean, it's. I really I really try to avoid to be specific about this. So we will in the main talk see that the interpretation of x and y are different. These are then states of quantum systems and not coordinates, and not necessarily. I mean, moments play an important role, yes, but it's not exclusive. It's a good example, though, to have in mind, yes.
Okay, and this kind of delay or integral or non-local nature that comes from the fact that somehow in these macroscopic coordinates, when someone implies independence of these coordinates, and these dependence is then tracked over the time evolution or in which way can I think of a delay equation or something like that?
Yeah, this is well, I do not have a good interpretation for this observation. So what you say, Dirk, is very reasonable. I have just observed that in fairly general terms, if you have, let's say, quantum, if you study the solution of the Schrödinger equation and you pass to a subsystem, then it is sort of inevitable that the equation of motion, if you don't want a loss of information, then is non-local in time. You get, so to say, the dependence of the past. And what people then usually do if you, so to say, kind of squeeze it into a differential equation of the type I mentioned, is known as a Markovian approximation for many models. Yeah?
Okay, so I see.
So Markovian means that there's no time delay then.
So thinking about statistical mechanics, I could think of, let's say, maybe the dispersion of molecules in a fluid, and that usually takes some amount of time. So if I then interact with the concentration or the density somehow of this, I would have a delay parameter in the effective system, I guess.
Yes, that's a good example. Here's another example. If you have a system of particles that interact with the radiation field, and you want to retain only the dynamics of the particles. Let's say you have a detector that sees only, can only detect what the particles do. Then the effective equation of motion of the particles that you get has such a memory, and in which all field configurations from the entire past enter then the dynamics.
Understand, yeah. Thank you very much.
Okay, so there are two more questions. Next question is Robert.
Hi, I have a question on the variational problem.
Yes.
You make any assumptions about the form of this auxiliary functional? Because otherwise you have always the trivial solution that you take the infimum of all the x that are given that are compatible with a y, and minimize the original functional, and that is, I mean, then you have no errors at all, right?
I do not really understand your point. Can you repeat it, please?
So I give you a functional of the y's, and that is for given y, find all the x's that are compatible with that choice of y.
Yes. Mm-hmm.
And then you take the infimum of the microscopic functional over those x, and that functional is of course trivially identical to the original.
Yes, so that's the idea of the Hohenberg-Kohn density functional theory, what you describe, and I would say it's, so to say, a mathematical possibility, but for usually it's not practical, because you need to compute. I mean, you need to have a explicit expression for the auxiliary functional then. So if you define it the way you described, then I mean, this is like the energy functional that Hohenberg and Kohn said it does exist, depending only on the density of the electrons, but nobody knows how it really looks like. And then there are clever approximations made. Yes, so you're right. I mean, at this point, I was deliberately vague so this would be a possibility that is not excluded by what I said. Yeah, so I should have a criterion that demands that the auxiliary functional is simple in some way. Yeah. Mm-hmm. Thanks. That's a good point.
Okay, thanks. So there's one more question by Sahand. Sahand?
Hi, I wanted to ask, these effective equations of motion, if you call them non-local, can you be more specific? What does that mean actually, the equation of motion for y is being non-local? And why is it being called like that? Just about this notion of non-locality that you are using, I'm not familiar with it.
Yes. One appearance of non-locality we had just described the non-locality in t. Yeah. So not only the time t enters then the right side, but if strictly speaking, then we have, so to say, times the entire past enters. But this is not what I meant. I mean, this is only one feature. The other is that if you have, let's say, you look at Schrödinger's equation for a wave, for the propagation of a wave function, then this is a differential operator, a second order elliptic differential operator. So that means we act with this operator on the wave function, and only at point x, only the properties in the vicinity of x, I mean of the wave function at x, enters the application of h to a vector psi. Yeah, because so there are only derivatives and multiplication operators that enter the Schrödinger equation. So if I apply h, the Hamiltonian, to a wave function psi, then h psi at x depends basically only on the wave function psi in a small neighborhood of the point x, because I mean I cannot just take the point x because I have to take derivatives also. Yeah, but that's the locality. And the effective theories then are more of the form nonlinear, I already said, but also they involve, let's say, integral kernels that link positions x to positions y rather far away in space. You know? So I think of x and y as spatial positions, or x1 and x2, and then these integral operators link the two variables, and so there is some what is it called, far action. I don't know, Fernwirkung in German.
Action at a distance.
Action at a distance, yeah, and this is well, some people say it's not physical, but it's kind of a consequence of this effective description.
Okay, just one follow-up question on this last thing you explained. So if there is this kind of integral dependence, but if the whole system is deterministic, it's just a relation between something that you could also change it by variable t or whatever. So it is. I mean, I'm a bit confused with this usage of non-locality. That if the solution depends on the whole path, then you call it non-local.
Non-local in time. Maybe that's not a good. Let me take it back. I think this is confusing. Let's just stick to a spatial non-locality in space.
Okay. Okay. Thank you.
Yeah. So this is what I meant.
Okay, thanks for that clarification. Okay, now I think it's fine sound. Yeah. Anyway, I think, yeah, we can now enter the core talk and start with the more technical part. So please can get on.
Okay, thank you. So let me come to the second half of my talk. I have. I would like to mix here a little bit my presentation with some handwritten drawings and writings. We'll see. So let's go on. So I would like to now come to effective theories for quantum systems. So we don't want to, I now go away from economy and general natural sciences. I'm interested in quantum mechanical systems. So let me recall some basic structural objects that we need. So we have in quantum physics a Hilbert space, complex Hilbert space H. I assume this to be, let's say, separable. And then the equation of motion in this case is the Schrödinger equation, as you can see in equation 5, is again in a linear initial value problem. The Hamiltonian H is a self-adjoint operator that acts on a dense domain. I will not mention any domain questions anymore further on, but here is the only point where I say that we are also looking at unbounded operators. And so that's the equation of motion given by Schrödinger's equation. One can argue that this is not the best description, and it's more appropriate to look at Heisenberg equations of motion, etc. But this is not the topic of my talk today. So let me just focus on the Schrödinger equation. And here, the static quantity I'm interested in is the ground state energy of the system. So this is really the lowest spectral point of the Hamiltonian. So the infimum of the spectrum of H. And by the Rayleigh-Ritz principle, this can be quantified as to be the infimum of all expectation values of H in quantum states sandwiched by normalized wave functions psi. Okay, so what is a typical H that I would want to discuss here? So I look for fermion systems. Let me first focus on fermion systems. It's not clear whether I will come to boson systems later, but let's first start with fermions anyway. So for an atom, then capital K is equal to 1, or a molecule, so then capital K is 2 or more, or in case of a solid, K is really the number of nuclei is really huge. We have a Hamiltonian which in second quantized notation, second quantized form, is given by equation 7. You will see that it's not just it's not just a means to torture you here with second quantized operators, but I will need them, and I cannot use the first quantized form. We will see it in a moment. So here the Hamiltonian comes in two pieces. There's a quadratic piece and a quartic part. And the quadratic term is usually called the one-body operator. And little h enters here this quadratic part with its matrix elements h, k, m. So these are matrix elements. If you go down for, can you see my mouse, by the way? Yeah. Yes. Okay, thanks. So H, K, M are the matrix elements of the one-body operator H in orbitals Fk and Fn. These orbitals are suitable orthonormal bases. Think of eigenfunctions of the harmonic oscillator, for instance. And V, K, L, M, N are the matrix elements of the potential V, the interaction potential, not the one-body part of the potential. Okay, so I specify the operators, the one-body operator and the pair interaction operator in equation 8. The one-body operator, let's look at this, contains two parts. There is the kinetic energy. This is minus Laplacian in suitable units. This probably multiples of 1/2 Rydbergs. And then we have the attraction by the nuclei. So the nuclei sit at positions R kappa and have a charge of Z kappa. And then if capital K is equal to 1, then we have just one nucleus, that's an atom. And if we have K nuclei, then and K is bigger than 1, then it's a molecule. Now, the nuclei are here static objects. They are just point charges at the positions RK. They don't enter the dynamics. And that's already a simplification. It's already an effective, a form of an effective dynamics, namely what is called the Born-Oppenheimer approximation would be to zeroth order. This would be the Born-Oppenheimer approximation. Anyway, the variables, the dynamical variables entering this system are the electrons, and they are represented by the creation annihilation operators acting on the vacuum. These gives us the wave functions of the electrons. And the one electron Hilbert space is this L2 space of R3 times the two spin states, spin up and spin down. Okay, so this is the usual model for an atom or molecule, and as you perhaps all know, it's impossible to compute the ground state energy, the number that I had specified in equation 6. Now, for this Hamiltonian, one cannot. Basically, it's already an unsurmountable problem to compute it, and we resort to effective theories and approximations made by these. So let me come to the effective theories here. So first of all, let me rewrite the ground state energy. So instead of taking the minimum over matrix elements of the Hamiltonian in wave functions with normalized wave functions, I can slightly more generally pass to traces of density matrices rho multiplied with a Hamiltonian. So then the ground state energy is the smallest expectation value of the Hamiltonian in any rho, and rho varies through the density matrices. So these are the trace class operators on the Hilbert space, which are positive and have trace 1. I do not want to consider here more general states in the CA star algebraic sense. This would lead us off. It's interesting, but it's not the topic here today. So these density matrices are then a subset of the trace class operators. And now I come to define the Bogoliubov-Hartree-Fock energy. So it is, it started out from the Hartree-Fock theory for atoms and molecules, and then including the contributions of Bogoliubov, led to a more general form of this approximation, which is now in the community often called Bogoliubov-Hartree-Fock energy. So here it is. It's defined simply by as the ground state energy in 9, except that we restrict the variation of the density matrices from varying over all density matrices to only varying over quasi-free density matrices. So the quasi-free density matrices I call QDM. So this is a subset of the full set of density matrices. And so let me explain to you what a quasi-free density matrix is. A density matrix rho is quasi-free if this is for the fermion systems, I should say. There is an analogous notion for the boson systems, but let me stick to fermions here. So density matrix is quasi-free if all odd moments in the creation or annihilation operators vanish, and all even moments can be computed from sums of products of pair correlation functions, pair expectation values. So here enters what Dirk has just mentioned before in his first questions. These are the states that are determined by their moments, by their second moments entirely. So the equation 13 is combinatorially a bit complicated, at least if the number R that determines the number of factors in the equation 13. If this number R is big, then this is a sum of this sum runs over many terms, but we are usually interested in small r. So typically r is equal to 1. This little r here is either equal to 1 or 2. So then the terms that occur here are easy to write down in a few lines. So anyway, this the sum on the right side runs through a subset of permutations, the subset being the set of pairings. So these are special permutations which have an order in the values of the permutation. So there are not so many as the full set. So no matter how complicated 13 may seem to be, it implies immediately that a quasi-free density matrix is completely determined by its one particle density matrix, gamma rho, and its pairing matrix, alpha rho, where gamma rho, I write down here in matrix elements, are the creation annihilation operator pair expectation values, and the pairing matrix are the annihilation operator expectation values. Note that for systems with conserved particle number, the alpha rho is always 0. So if the density matrix commutes with the particle number operator, then alpha rho is always 0. There never are the particle number sectors mixed by the state. And in fact, this is the case if we apply the Bogoliubov-Hartree-Fock approximation to the model with the atoms, what we had before. So in this case, if we apply it, then we obtain, for the expectation value of the energy, we obtain a new functional. This is the auxiliary functional in the theory I'm looking at, is the Bogoliubov-Hartree-Fock functional. It depends only on gamma rho, and it is given by equation 15. So there's a trace of the one-body operator with a one-particle density matrix. And then there is the pair interaction term, and it has two contributions. The first contribution, in the first contribution, you see the term gamma rho XX and gamma rho YY. This, if you work it out, is the product of the one particle density of the system at X times the one particle density at Y. I I refrain from calling it rho of x and rho of y, because then we have too many rho's flying around here. So let me stick to this gamma rho xx and gamma rho yy. So this is in fact the classical electrostatic energy of the fermion gas if we interpret its one particle density as a classical charge distribution. But there is a correction, there is a quantum correction to this term, and that's the second term here, where we subtract the gamma rho at xy to absolute value square. And this is known in quantum chemistry as the exchange term. It has a negative sign because we are looking at fermions. If we were studying bosons, this sign would be a positive, would be plus sign. And it is very important for the theory of chemical binding. I believe that if we analyze the Bogoliubov-Hartree-Fock theory in its own right, as I had said before, if we assume that it's a good approximation and we study the predictions that we get from the Bogoliubov-Hartree-Fock theory, then we will see that the chemical binding of the molecule with K nuclei is crucially depending on the exchange term, the last term in the integral in equation 15. All right, so that's the energy functional, and then clearly, if we insert this, then the Bogoliubov-Hartree-Fock energy, the infimum of this functional, is then the infimum of the energy functional, and it turns out that the one particle density matrices, it varies over all one particle density matrices, but this set of one particle density matrices, gamma sub rho, can be very simply described. Namely, these are all trace class operators which have eigenvalues between 0 and 1. So we obtain a simple formula for the Bogoliubov-Hartree-Fock energy is the infimum of the Bogoliubov-Hartree-Fock functional for density matrices, fermion density matrices between 0 and 1 and finite trace. The latter to ensure that we have finite values of the functional. All right, so what can we, let me add a bit of a discussion here. So the particle number, you may miss that I'm not fixing the particle number here for the system. I'm working in the grand canonical ensemble right away. But if it is necessary to fix the particle number to a specific value, we can add a chemical potential and adjust it so that the particle number comes out in the right order that we want to have it. Now, if we look specifically at atoms and molecules, then there are good error bounds on the on the difference between ground state energy and the Bogoliubov-Hartree-Fock energy. So let me comment here a little bit on what the contributions have been. The leading order and even all contributions to the Bogoliubov-Hartree-Fock energy are accurately described. Or let me put it the other way, that all contributions to the ground state energy is accurately described by the Bogoliubov-Hartree-Fock energy up to small errors. That is, in fact, a result of myself from some 35 years ago. And then there has been, I mean, for atoms and molecules, but then there has been studies of other systems, like also in particular condensed matter systems, where similar, where one can take advantage of the translation invariance of these systems, and then there have been also almost 35 years ago very good results by Graf and Solovay, and then let me jump to the present. These approximations have been justified even to higher accuracy than what the Bogoliubov-Hartree-Fock energy describes by a recent work of Nam, Christiansen, and who's the third? Christian Heinzel, I suppose. So they can push the correction to the next term in the expansion of the energy. Also, there has been by Levine, Gontier, and Heinzel, I think there has been a very good and interesting result that the deviation of the ground state energy from the Bogoliubov-Hartree-Fock energy can at most be exponential in the perturbation parameter. That's also a very interesting result. Now, let me come to the questions, what do we know about the state? So this is all work. I mean, a lot of work has been invested in quantifying the error of the energy values. But then what about the state? So here one can say that the one particle density matrix of the ground state density matrix and the Bogoliubov-Hartree-Fock density matrix, these are close to one another. So their L1 norm is for a large system much less than the number of the particles in the system. I'm being, I have to say, a bit vague. This applies to systems with a large nuclear charge. And then there are also many results from the past let's say 20 years or so on the question whether the Bogoliubov-Hartree-Fock theory gives rise to a good dynamical approximation too. So there is what is called the time-dependent Hartree-Fock equation, which I have mentioned here in the middle line of this bullet point. So this is a differential equation, an evolution equation, nonlinear evolution equation for the one particle density matrix. It looks a little bit like the Heisenberg equation of motion, but the derivative of the density matrix in terms of the commutator with the Hamiltonian. But here, the Hamiltonian itself depends on the density matrix, is an effective Hamiltonian, and so this equation is nonlinear. Nevertheless, one can, solution, existence and global existence and uniqueness of the solutions and properties of these have been established in the past. And also it has been proved that at least for small times, this approximate evolution, so this time-dependent Hartree-Fock theory solution, stays close to the one particle density matrix of the full Hamiltonian, the full evolution. The error term is small. Well, here I'm missing a factor of t, I notice now. It stays small, but only for small times. So if you see the the function here on the right, then it's the exponential of an exponential. So the right side grows in t very rapidly. So such an estimate by the techniques that are used so far is good only for very small times. So there has been a lot of work done on this question here. Let me mention that one group that has been contributed a lot is the one around Christian Heinzel and his group in Munich. Christian Heinzel, some parts in collaboration with Mathieu Levin or Robert Seiringer. And then there is another a big group that works on various instances of this, and that's led by Benjamin Schlein in Zurich. And they all have results of this type with some optimality in one or other. Let me say, rather than what is still open, in my opinion, namely, I think there's the picture of what should emerge for large times is totally unclear. That is what we get here is a small time approximation, and we know a priori that for large times the system converges weakly to its ground state in some sense. So we have this as a result that we know a priori, and a scattering theory would be needed to bridge the, so to say, t equal infinity to t small solutions to this approximation. It's a very difficult problem, obviously, but it's open. This is what I want to say. And then finally, let me mention predictions that are derived by the Bogoliubov-Hartree-Fock approximation about phases of statistical mechanical systems. So one such system, which is still simple enough that one can analyze the Bogoliubov-Hartree-Fock theory, is the Hubbard model. And here one can, for instance, see that the Hubbard model at half filling in the BHF approximation is always antiferromagnetic, as it should be. As it is expected to be, let's say, and that for low filling and large coupling, the Hubbard model, the Bogoliubov-Hartree-Fock approximation for the Hubbard model leads to a ferromagnet, a saturated ferromagnet, in fact. So one can draw as a rule of thumb the conclusion that the Bogoliubov-Hartree-Fock approximation tends to overestimate the reaction of the system, to overestimate the order parameter. So it yields antiferromagnetic order where one may or may not really expect it, and likewise for ferromagnetic order. It kind of over amplifies the effect. I cannot make this mathematically precise. So what I had just cited is work by Lieb, Solovay, Travaglia, and myself in the past 30 years. But there's also, and that I would want to mention, there's also a very recent work, not so recent, and then even very recent work by Edwin Langmann in Stockholm and his collaborators. So let me advertise for a recent paper of Langmann and Lennartz, Jonas Lennartz and and then with other co-authors entering various papers, and they analyze. They give for some instances of the Hubbard model a full phase diagram by their analysis of the Bogoliubov-Hartree-Fock approximation. So it's a mixture of a very interesting blend of mathematically rigorous analysis and numerical analysis. So I think this is a great effort, and they have very good results. These people. So that's what I wanted to say about fermion systems. Now, this would be a natural point to stop if time's up. Paula, let me ask how we are doing.
Depends on you if you have a short part still left. I mean, there's a couple of minutes left. So if you want to continue, I'm not sure.
Okay, well, I don't want to torture the people here. We said, okay, so we started at 1 hour ago, so maybe 10 minutes would still be okay.
10 minutes would be perfect.
Okay. So I would let me first, because I think this is something that is not so much known, let me first come to the quasi-free states in general, and let me switch to a little notepad here. So I would want to change to this. So can you see my external pad now?
Yes.
Okay, very good. So I switch off my camera for the moment, because I flipped the screen. So I would like to do some drawing of the way I think about quasi-free states and the density matrices. So imagine that we have the whole canvas here is a set of all density matrices. So this is the DM I had before, and then the quasi-free density matrices are a subset of this, but the subset has a structure. I mean, some people say it's a manifold. I don't like to call it a manifold. Maybe it is a manifold, but when I have a manifold, I think of charts and this sort of thing. Anyway, so here it is, in fact, a manifold, the way I draw it, one-dimensional and a two-dimensional. So it's a lower dimensional manifold. And we have all density matrices here in the plane. So let me pick one. So here is a density matrix. This is rho. And then here comes a very important part. We have seen that the density matrix can be quantified by characterized fully by its one particle density matrix and the pairing operator. And if we are given a one particle density matrix and a pairing operator, then we can construct a density matrix, a full density matrix on the set of density matrices, which is quasi-free. So this defines a kind of a projection. I call it Q of rho. Q of rho is known as the quasi-free projection of rho. So now the picture I'm drawing suggests that rho and Q of rho are close to one another. I mean, this is not really fully justified, but a little bit it is. So let me first stress again, what is Q of rho? It's a map. So we take a density matrix rho, then we compute the one particle density matrix and the pairing operator. So we get rho, we compute gamma rho, and alpha rho. And then from this we get a Q of rho, which is a quasi-free state which has the same one particle density matrix and the same pairing operator. And that's my Q of rho. And this, in fact, acts as a projection on the space of density matrices. So Q square is equal to Q. If we reduce it to the quasi-free ones, then we reducing it again doesn't change things. Now, so this is a nice picture, and then we can start to look at the time evolution. So here we have, let's say, the initial value rho of 0, and then here's the initial value of the quasi-free density matrix. And then as time evolves, we move here, and we get to a point rho of t. That's another density matrix. And we again find the Q of rho of t to be the point on the quasi-free ones that derives from rho of t. So this would be, so the Q of rho is really the function that I had in mind in the introduction, in the perspective part, which I called the capital Y. Yeah, so we get a simpler object from the more complicated one. The Y, the variables from the more complicated. And so the question is, if we have, let's say, the time-dependent Bogoliubov-Hartree-Fock evolution, then this would also start at Q of rho 0 and would take us perhaps here. It stays quasi-free. And so then the question I asked before would be, is this small, this distance? Yeah. So that would be, so to say, pictorialization of the question whether the approximation is close to the to what we get from the full evolution. Now, so these are nice pictures, but the question is, can we make this more substantial mathematically? And there's one important observation that I want to that you may or may not know, that was made by Mauser and Gottman, I think. Gottman and Mauser. In 2008. And they had the following observation. Let me put it here. They observed that if we take for a measure the relative entropy, so the relative entropy of the state rho relative to Q of rho, the quasi-free projection, then this is the infimum of all quasi-free rhos. Let me call it here rho Q, or maybe rho tilde is better visible, dm. So all relative entropies, if we let the second argument run through all quasi-free density matrices and look at the relative entropy, then it is minimized by the quasi-free projection. So that justifies here in the picture that the distance, if I want to, so to say, interpret here this geometrical projection of the black point onto the blue line. Yeah, why don't I project it? Let me just give an alternative. Could it be that the projection is, leads us here? Is this maybe a better way of describing Q of rho 0? And the answer is no. If we interpret the length of the black line here, the length of this black segment to be the relative entropy of the density matrices, then we have to take the point on the blue manifold which is closest to the black point rho of 0. So this is something, I think this is a very nice interpretation I'd like to make. Yeah, so maybe this is a good point to stop here at this moment.
Okay, thank you very much for this nice talk and for this up-to-date perspective on this field of effective equations.
Let me mention that I can and will provide references in a write-up. Yeah, I didn't list them here not to mess up my talk with too many citations mentioned.
Yeah, sure. We could even, we can discuss that later. We could also share the slides if it's fine for you. Depending.
That's fine for me, sure. Mm-hmm.
Okay, so let's start the Q&A. So first hand is up. So Michael, you have the first question.
Ja.
Hi, Michael.
Hallo Volker, schön dich zu sehen.
Ja.
Okay.
Let's
switch to English.
Yes.
How would the recent work of Ian Jauslin and Elliot Leap fit in there? So they have this, what they call the big equation and the small equation for this Bose-Einstein condensates, and they work with a Bogol-Lyubov approximation to begin with, and then they do another approximation, and numerically it is remarkably accurate apparently. And so how does that fit into this story?
Just candidly, I don't know, Michael. I haven't looked into this work.
Okay, so I can send you the references.
Yeah, thank you. Mm-hmm. That would be great.
Okay. So the next question is by Aritro.
Hi, thank you for the talk. That was really informative. I had a few questions about the dynamics, actually. Not so much as the ground state minimization problem, but what happens dynamically in time. And basically, I wanted to ask if the Bogoliubov-Hartree-Fock method, if you said something about it not being so great for long times, if you could comment on that. And secondly, I had two questions regarding this expectation that we as physicists kind of have that under unitary evolution of this quantum state, of this quantum system, the system should kind of go towards the ground state, free energy minimization. Is that a realistic expectation? Because I feel like under unitary evolution, this should probably not be the case because energy is conserved. So whatever energy the system starts off with, the initial that should remain. So the entirety of the system cannot relax into the ground state. So if you could comment on that, and also that because there are correlations, these correlations would also not die off. So how good is this quasi free method with regards to this, basically? Thanks.
Okay. Okay. So that's these are very good questions. Let me start with the last question. Yeah? Okay. So the last question was about the long-time behavior and the relaxation to the ground state that I mentioned. You're right. If the system under consideration is closed, so for example, if we are on the torus spatially, then energy is, so to say, conserved and cannot escape to infinity. So for this relaxation to the ground state to happen, it is necessary that the system is open. So we have a component with a continuous spectrum, or at least, non-trivial essential spectrum, as opposed to a system which is confined in say on a torus, and we have a purely discrete spectrum. And then, this has, let me comment on this a little bit. I have, together with Frederick Klopp and Heribert Senk, who's actually in Munich, you may know him, we have analyzed the photoelectric effect. And if, which is a customary approximation, if the radiation field is discretized on a torus, then there is no photoelectric effect, strictly speaking. Maybe if you wait long enough, then the photons that would, the one photon scattering is not more important than the, say, 3, 4, 5 photon scattering, because all photons come back eventually if we wait long enough. And so then one can compute that the photoelectric effect in this case would be classical. It would really be, the intensity would be the decisive parameter, not the frequency. Anyway, that's a side remark. So the answer to your question is we need an open system for the relaxation to the ground state to happen. And then you ask, so what happens then to the correlations? Well, I think this is very difficult to say. If the system is open and things fly apart, then indeed the scenario is that we have clusters of particles that move freely in space and don't interact with one another. And so they have some internal complicated dynamics, which could be in form of a bound state, or some additional rotation or so, and then free motion, and there's no there's a very fast decay of correlation from one cluster to another cluster. That's what is expected, but it's very hard to make this into mathematics, really. I think it's, at the moment, impossible. But conceptually, it's clear what one would want to do. And then you ask a question about the short-term approximation. So I would say the methods that have been applied to control the deviation. We have two different laws of motion, one for the effective theory and one for the full theory. And then what naturally happens is that they, if they start together with the same initial value, they start deviating in time. And it turns out that this is, the best one can bound is that they evolve. They deviate exponentially from one another in time. That doesn't mean that the energies are very different or so, but there's just no mathematical control on this approximation anymore. That's what one can say. And I think this is in part so to say, a technical problem of the method that is being used. So what people use in this business and the mathematics are in one way or other variants of the Grunwald inequality. So that is the tool from ordinary differential equations. Peter Pickel has developed some 15 years ago a very powerful variant that led him to gave a very good analysis on the very good control on the evaporation, so to say, of bosons from a Bose condensate, and from there on, many variants of this idea have been developed. I think this is paper in LMP of Peter Pickel from 2010, perhaps.
Okay, thanks. I think there's a follow-up question, or
yeah, there's a few follow-ups. Thank you again for the very enlightening answers. Yes, indeed, of course, in a closed system, energy will be preserved. So there's no way that like a closed system can actually go towards the ground state. But I'm a bit confused, maybe because I'm coming from the physics angle, more about the spectrum that you mentioned. I believe that like a closed bounded system will indeed have a discrete spectrum, but
yes.
But if there is yes. So but if there is a continuum, does that automatically mean that it is an open system? I do not think so, because this is also a question that one poses in spontaneous symmetry breaking. Perhaps in the thermodynamic limit, there also one considers systems which are closed in some sense. There's so perhaps my question to you is that like what about those systems which do have a continuum spectrum but which are not open? Does that make sense?
Yes, I mean, there's no, I didn't mean to say there's a one-to-one relation between these two properties. I just wanted to make clear that if you want to have relaxation to the ground state of the system, in the sense that you can prove whatever initial state you start with, and we are at 0 temperature here, whatever initial state you start with. So it's not a thermal relaxation, it's a dynamical relaxation to the ground state, and this needs some, so to say, some door which is open to escape to infinity for the states. And I would say this typically comes about with a continuous spectrum of the system, but it's not one-to-one. Certainly if you have a discrete spectrum, then there is no dissipation here, or dispersion.
Just my last question, and then I'll stop. What about spontaneous symmetry breaking then? Because usually in spontaneous symmetry breaking, people are interested in, well, they write down the Lagrangian, and it's kind of understood that it's people work in closed setups, even though it's not mentioned perhaps like explicitly, and one expects that dynamically there's going to be a state which is a superposition of two symmetric states would dynamically spontaneously break that symmetry. That seems not possible, actually, under unitary.
This is so to understand in full for the full interacting theory, symmetry breaking, spontaneous symmetry breaking is a very complicated matter. And it sure cannot be be done by energy considerations. So there are other properties of the model need to enter. But this is a side remark. Let me come to the Bogoliubov-Hartree-Fock theory. I think one of the advantages of this approximation, people in physics usually laugh at this and say, well, we know what this means for 90 years. What can you tell us new about anything? Well, the truth is that for systems which are very difficult to analyze, is there symmetry breaking or not? the BHF theory opens a door, a road to decide on this. Yeah, it amplifies symmetry breaking, but it gives an indication. So, for instance, if you, let me just direct you to the paper of Lennels and Langmann on the Hubbard model. They have really drawn a phase diagram, and I think it's in good agreement to what the theoretical physics community believes is correct. And their phase diagram derives from the Bourgeois-Hartree-Fock theory.
Just the ground state minimization methods, right? No dynamics, right? No time-dependent stuff.
Yeah, it's just static, and I think it is at zero temperature. Most of it is at zero temperature, but maybe they also have some parts with positive temperature, and then they quantify the transition temperatures of whatever magnetic order or whatever occurs.
Thank you so much.
You're welcome.
Thanks. There is another question by Dirk.
Hey, thanks, Paula. Thank you very much, Volker, for the wonderful talk. I soon have to run to my other student seminar, but I'd like to ask at least one question. Maybe you can comment a little bit on this. Also towards this dynamical comparison between this effective evolution and the true evolution. So if you look at these results for Bose gases, for example, they consider many different types of scalings. I think everyone wished to do the thermodynamic limit, but there's also a low density or high density limit and so on and so forth. In this estimate that you show, which is like c times time times e to the ct, the constants are just order 1 in the number of particles, and or are there some good scaling parameters in which these constants could become small in order to extend the length of the validity of the estimate? Could you comment a little bit on this? I'm completely ignorant on this field. So.
Oh, well, now you got me, Dirk. I think these estimates of this form are usually formulated for some scaled models, scaling limits. So the particle number enters in an inverse power as a coupling constant. Or rather, the coupling constant is an inverse power of the particle number by rescaling the spatial and temporal variable. And then it's not so easy. You have to, so to say, compare result by result. What do the error bounds really mean? So I think there are very good results around. Let me also mention that there's also the group of Niels Benedicter, who has produced for Fermion system excellent approximations. These results, it depends on the context, and often it is not clear to me whether the interaction even is contributing to the dynamics. So or put it the other way around, don't you get the same result if you just leave out the interaction? If you just dismiss the interaction potential, it could be that for a coarse version of this bound, you get the same by just comparing the dynamics with the dynamics of the free Schrödinger evolution, which is also explicitly soluble. And so this has to be case by case studied. So I don't know a kind of a general answer where these constants enter. Where these constants in the estimate are of order 1 in which scale. It's not. There's no general answer to this, I think.
Okay, and maybe a last quick follow-up question, like comparing the Coulomb term to the Fermi repulsion. Can you comment a little bit on how much, which of the mechanisms contributes to the dynamics or to the ground state energy more? For example, I mean, exactly what you just said. I mean, somehow the Fermi repulsion, yeah, gives already a very large, I think, mechanism, even I think compared to the Coulomb potential, to change both the dynamics and also the ground state, of course. And this is something that we can't switch off or can't scale with the coupling constant and so on.
Yeah. So I cannot give a quantitative answer to this. I can only, so to say, share a feeling about this. I think that the so to say classical parts of the interaction that one retains usually is like a background, even though it's very singular. It does not really influence the quantum character of the system, whereas the exchange terms or general correlation really can, so to say, lower energies by doing complicated fermion arrangements, and there's a fermion repulsion, as you mentioned, that forbids to have parts on the same point, etc. So this is the way I think about this, but I do not have a quantitative bound. I mean, usually if you count the contributions to the total energy, then the classical contributions are the biggest ones. But what we're interested in when we study binding are the energy differences what is the gain by moving the parts together or apart, and that's a more complicated matter.
Understand. Okay, thank you very much.
Okay, so there is one more question. I think we should make it's the final question, and Robert, you can.
Okay, so maybe it's more speculative or philosophical, if you like. So you explained to us that for these Hamiltonians with 1 and 2 particle parts, the quasi-free states are good approximations, both for the ground state and for the dynamics. And this reminds me a bit of spin chains, where often enough we know, or people use in numerics, that tensor product states or states of finite entropy are good approximations for the ground states. Could you dream of some generalized theory that for some, we come up with a class of Hamiltonians and you tell us what is a good small dimensional submanifold of states that are good approximants?
That's a very interesting question. In fact, many people are dreaming of kind of bringing these things together. There's a certain barrier that the quasi-free states have no simple generalization. One can, and the relation to tensor product states is not simple either. So the answer, the frank answer to your question is I don't know. But people are really, the mathematicians are dreaming of finding, a kind of a new set of effective variables that can be have such a powerful and computationally accessible is a tool like the quasi-free states. So the answer is again, I don't really know. There were also speculations about what is known as free probability, that this could be the key to new set of states. But so far, I haven't seen systems that have been whose let's say properties have been analyzed and made explicit by using these these states from free probability. Yeah.
Thank you.
Okay, so I think we have here a very short, very last final question, Arito. I don't hear you. Maybe there's something.
For the last question,
Yes,
I had a quick question. The context of the question is again dynamical in time, and again like something which has to do with spontaneous symmetry breaking or near the critical point, and it is kind of well known from very static arguments that near the critical point, correlations would kind of diverge. So the states which are playing the game, so to speak, have these large correlations, so macroscopic superpositions in some ways. And what exactly is known about this dynamics through this critical point? Like, can one use these kind of effective Bogoliubov time-dependent methods or perturbative methods, or do they all break down?
They all break down. I mean, this is. I think this is not, so to say. That's not the method of choice here. What you would then and what is done is to apply renormalization group schemes to get close to the critical point. And that's also an effective theory, one that I had liked to talk about too, but the time runs out. So with the renormalization group analysis, one can make quantitative predictions on the correlation length and these sort of things.
Not the dynamics, right? Like, it's not going to tell us anything about the dynamics. Like, as far as I know about the renormalization computations, they don't really tell us anything about the dynamics.
Yeah.
You can constrain and like do all kinds of stuff, yes, but dynamically, like what is happening, I don't think.
Yeah, I would be very cautious to apply I mean, this Bogoliubov-Hartree-Fock theory is simple and fairly rough, fairly coarse. And so I would be cautious to say something in the vicinity of whether this has anything also dynamically in close to the critical point.
Okay, thank you so much.
Okay, then I think this is a good point to stop the Q&A. So thank you again, Volker, for coming and for.
Yeah, it is a pleasure. Thank you.
And
yeah, thanks, Volker, for having you here. It was a great finish of our this year's.
Yeah, that's right. Now
winter and spring series.
Semester is over.
Yeah. Okay, that was a wonderful talk. Thank you so much for.
Thank you very much. Yeah. So thanks to everybody for coming. I really appreciate that.
Yeah.
All right.
So
then I don't know, how many weeks do you have left in the semester?
Only this one. So on Friday it's over, so to say.
Okay, then we have a bit time for research again.
Yeah. Well, next week I have a lot of exams.
Yeah, me too. Yeah.
Okay.
Okay, I guess all.
Okay.
Was really a lot of fun and pleasure, and we're going to keep you all posted for the next series. It's going to start in the summer semester, but we are still in the preparation. But we'll keep you posted. Thanks for coming around. Have a good time. Be safe, and see you soon in good health.